In modern times, we built giant telescopes that have allowed us to cast our gaze deep into the universe. Astronomers have been able to look back to near the time of its birth. They've reconstructed the course of cosmic history in astonishing detail. From intensive computer modeling and myriad close observations, they've uncovered important clues to its ongoing evolution. Many now conclude that what we can see, the stars and galaxies that stretch out to the limits of our vision, represent only a small fraction of all there is. Does the universe go on forever? Where do we fit within it? And how would the great thinkers have wrapped their brains around the far-out ideas on today's cutting edge? To begin to get a handle on infinity, we're going to need some perspective on the numbers and scales that define our universe. One place to start is a narrow side street in Charles Dickens' London. A curiosity shop, fictional to be sure. Here you can find an unparalleled collection of stuff. Old shrunken heads, manuscripts, newspapers, books, and rare examples of impressively large numbers. From Zimbabwe comes a $100 trillion note. In late 2008, with that nation battered by hyperinflation, it was worth about $1.50 US. Go up 2 orders of magnitude to something decidedly more useful. The fastest supercomputer in history will soon hum along at 20,000 trillion calculations per second, a 20 followed by 15 zeros. You'll have to run it about a day and a half to equal the number of grains of sand on all the world's beaches. That's around a sextillion, a 10 followed by 22 zeros. That's roughly the number of stars in the visible universe. Atoms in the visible universe? That's upwards of 10 to the 78th power, a 10 with 78 zeros. Cubic centimeters? A mere 10 to the 84th, a septuagintillion. To go up from there, return to no less a source than the Guinness Book of World Records. The largest named number in regular decimal notation, the Buddhist time period Asamkhya, is 10 to the 140th years, or 100 quintoquadragentillions. Then there's the largest number ever used. Graham's number is a calculation of angles in a type of hypercube. If you divided the visible universe into the smallest units known, called Planck volumes, the total of those units wouldn't get you anywhere close to Graham's number. But it's still nowhere close to the ultimate ceiling. Infinity. For those who find infinity hard to grasp, even troubling, you're not alone. It's a concept that has long tormented even the best minds. Over 2,000 years ago, the Greek mathematician Pythagoras and his followers saw numerical relationships as the key to understanding the world around them. But in their investigation of geometric shapes, they discovered that some important ratios could not be expressed in simple numbers. Take the circumference of a circle to its diameter, called pi. Computer scientists recently calculated pi to 5 trillion digits, confirming what the Greeks learned. There are no repeating patterns and no ending in sight. The discovery of the so-called irrational numbers like pi was so disturbing, legend has it, that one member of the Pythagorean cult, Hippasus, was drowned at sea for divulging their existence. A century later, the philosopher Zeno brought infinity into the open with a series of paradoxes, situations that are true but strongly counterintuitive. In this modern update of one of Zeno's paradoxes, say you have arrived at an intersection, but you are only allowed to cross the street in increments of half the distance to the other side. So to cross this finite distance, you must take an infinite number of steps. In math today, it's a given that you can subdivide any length an infinite number of times, or find an infinity of points along a line. What made the idea of infinity so troubling to the Greeks is that it clashed with their goal of using numbers to explain the workings of the real world. To the philosopher Aristotle, a century after Zeno, infinity evoked the formless chaos from which the world was thought to have emerged, a primordial state with no natural laws or limits, devoid of all form and content. But if the universe is finite, what would happen if a warrior traveled to the edge and tossed a spear? Where would it go? It would not fly off on an infinite journey, Aristotle said. Rather, it would join the motion of the stars in a crystalline sphere that encircled the Earth. To preserve the idea of a limited universe, Aristotle would craft an historic distinction. On the one hand, Aristotle pointed to the irrational numbers such as pi. Each new calculation results in an additional digit, but the final number in the string can never be specified. So Aristotle called it potentially infinite. Then there's the actually infinite, like the total number of points or subdivisions along a line. It's literally uncountable. Aristotle reserved the status of actually infinite for the so-called prime mover that created the world and is beyond our capacity to understand. This became the basis for what's called the cosmological or first cause argument for the existence of God. Another century later, Archimedes incorporated actual infinity into measurements of curved lines and volumes. His method boils down to a process of summation. Place a triangle inside a circle, turn it into a square, then a pentagon, and so on. As the number of sides increases to infinity, their combined lengths equal the circumference of the circle. By slicing and dicing curves into an infinite number of straight lines, he was able to compare a variety of curves, areas, and volumes. Archimedes anticipated techniques developed 2,000 years later. And yet his ideas on infinity did not carry forward due to what the author David Foster Wallace described as a mathematical allergy that developed in response to Aristotle's potential infinity. It was Aristotle's ideas that passed into the Christian era, along with his cosmology, with Earth seated firmly at the center. That view was not universal. Islamic, Hindu, and even some Western thinkers posed alternate views that included infinite space. In European circles, the issue of infinity resurfaced during the Renaissance. In 1543, the Polish astronomer Nicholas Copernicus argued that Earth orbits the Sun, not the other way round. The old Greek spheres began to fall by the wayside when a distant supernova, then a comet, were spotted by the astronomer Tycho Brahe. These objects seemed to behave independently of the other stars. A monk named Giordano Bruno inflamed the issue by traveling Europe at the height of the Inquisition to proclaim an infinite universe. In the year 1600, he was burned at the stake for this and other heresies. Just 9 years later, in 1609, Galileo Galilei used the first astronomical telescope to show that the universe is much larger than we thought. In later writings, he even sought to discredit the distinction between potential and actual infinity. Galileo was forced to recant, and the old Aristotelian view held sway. Any attempt to assign a value to infinity, in numbers or in nature, was doomed, for that was the unique province of God. Finally, at the end of the 19th century, the mathematician Georg Cantor sought once and for all to divorce metaphysics from the abstract pursuit of math. Infinity, he wrote, had to be studied without arbitrariness and prejudice. He became known for folding finite and infinite numbers into a unified theory of number sets, considered a foundation of modern math. One of his defenders used a paradox to show how infinite sets are subject to concrete comparisons. Say you've come to stay at this grand hotel. You're in luck because here there is an infinite number of rooms. Oddly enough, you learn there are no vacancies. Fortunately, the manager says, "I can still check you in." He assigns you to room number 1 and directs you down the corridor.
Wonderful. Thanks.
Then he goes to work, shifting the guest in room 1 to room 2, room 2 to 3, 3 to 4, and so on. So in this hotel, there's a number set that includes an infinite number of guests and rooms. Then there's that same set plus you. 2 infinite sets, yet one is a subset of the other. Being able to use infinite sets of different sizes allowed mathematicians to design equations describing continuous motion and change over time. Echoing Aristotle, a critic of the new set theory suggested that the end of the corridor is still only a potential infinity, with God representing the only actual infinity. For those who pine for humble accommodations, we'll recommend an alternative later on. Even as mathematicians embraced infinity, astronomers in the early 20th century still saw a limited universe, centered on the galaxy, a flat disk of stars. Did the limits of our vision, like the horizon at sea, conceal an infinite universe beyond? Albert Einstein, for one, believed that if that were true, then the night sky would be filled with dense starlight shining from every direction. We'd reel from the effects of infinite gravity. Arguing for a finite universe, he described a people living on the 2D surface of a sphere. To them, a beam of light moving through space would appear to go straight on an infinite journey. In fact, it follows a path determined by the overall gravity of the universe and curves back around. Like the old Greek spheres, this view of a static and limited universe began to fall by the wayside in the 1920s. Edwin Hubble and Milt Humason used the new 100-inch telescope on Mount Wilson in California to look at mysterious fuzzy patches of sky called nebulae. They found that these patches were galaxies like our own, and that some were very far away. What's more, they found that most are moving away from us. The farther out they looked, the faster the galaxies are moving. This fact, known as Hubble's law, led to an inescapable conclusion that the universe is expanding. Furthermore, if you run the clock back on this expansion, it appears that it all began in one singular moment. That moment has traditionally been described as an explosion. A Big Bang. How large the universe has gotten since then depends on how long it's been growing. and how quickly. Using an array of modern telescopes, astronomers have recently narrowed the beginning to 13.7 billion years ago. Taking into account the expansion of space ever since, the radius of the visible universe, the part we can see, has expanded out to 46 billion light years. These measurements have raised anew the ancient questions. What's beyond our cosmic horizons? Is there an edge? Or does it somehow go on forever? A new set of answers has emerged from a theory designed to address questions that arose from the original model of the Big Bang. For one, how did the universe get so large? The Hubble Deep Field contains images of infant galaxies at less than 10% of the age of the universe, near the edge of our cosmic horizons. By the time one of those galaxies reached maturity, it would have moved far, far beyond our horizon. And what of all the galaxies visible at its horizons? For another, how did the universe get so smooth? In every direction you look, the density of galaxies is the same on large scales. Astronomers believe that whatever process flung the universe outward must have also blended it in its earliest moments. The theory that addresses these questions was based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposite charge, matter and antimatter. The idea is that in primordial times, an energy field embedded in this so-called quantum vacuum suddenly moved into a higher energy state, causing space and time to literally inflate. And our universe to burst forth. If this theory is right, then our universe is incomprehensibly large. Its author, the scientist Alan Guth, wrote that the universe as a whole would have grown to at least 10 billion trillion times the size of our visible patch. That's a 10 followed by 23 zeros. If you think that's big, a variation on the theory describes the origin of our universe as a physical process that exists far beyond it, out into the seemingly infinite void that had confounded Aristotle and other Greek thinkers. In that case, our universe would have inflated like a bubble and joined a stream of other bubble universes frothing up and expanding across an endless ocean of time and space. A related idea theorizes a cosmic landscape unfolding in vast fractal patterns. These new, more expansive visions of the cosmos are not without their paradoxes. Logically speaking, with infinite stars, infinite planets, infinite universes, you will also have infinite possibilities. The so-called infinite monkey theorem has its roots in Aristotle's attempts to illustrate the perils of thinking about infinity. Ask a monkey to type, or ask an infinite number of monkeys to type, for an infinite amount of time. You're sure to get a lot of random letters. But there is a chance, however small, that somewhere, somehow, you'll get the full text of Shakespeare's Hamlet. It's clearly absurd. Then again, consider the increasingly strange nature of our universe, as suggested by some new observations. This is where we draw your attention from the famous Hotel Infinity to a less well-appointed alternative. You're sure to get a big welcome at the old Hall of Mirrors. This ramshackle place would have thrown even the great thinkers for a loop. It represents a kind of optical illusion that may be present in our view of deep space, according to a new interpretation of data from one of the most important space satellites ever launched. WMAP was sent out to make precision measurements of radiation left over from a period about 300,000 years after the Big Bang. It revealed an intricate pattern of hot and cold spots, now thought to represent the seeds of the galaxy filaments and walls seen on large scales. The pattern was laid down by pressure waves that ricocheted through the expanding gas of the early universe. One group of scientists, looking at the sizes of these waves, suggested that some are actually mirror images of themselves. From this, they argue that the universe could be much smaller than we think. That's not the only strange new line of evidence. Tracking the movement of distant galaxies, astronomers found huge clusters moving at about 2 million miles per hour in the direction of the constellation Centaurus. With the results published in a top scientific journal, the astronomers describe an immense gravitational presence that may loom beyond our visible horizon, perhaps another universe that inflated near our own. Ideas like these may well have led to imprisonment or death in centuries past. Now they're a part of a field of study that is bursting with data and ideas. Cosmology, the study of the universe as a whole, has long been infused with metaphysics and philosophy. Today, it's steadily merging into the physical sciences. So, is the universe infinite? Scientists will continue to look for evidence of what lies beyond our horizons, and to test theories on the nature of time and space. But like the room at the end of an endless corridor, the final answer will always elude us. Breed of black holes that has reached incomprehensible size and destructive power. Just how large and violent and strange can they get? A new era in astronomy has revealed a universe long hidden to us. High-tech instruments sent into space have been tuned to sense high-energy forms of light, X-rays and gamma rays that are invisible to our eyes and do not penetrate our atmosphere. On the ground, precision telescopes are equipped with technologies that allow them to cancel out the blurring effects of the atmosphere. They are peering into the far reaches of the universe and into distant cauldrons of light and energy. In some distant galaxies, astronomers are now finding evidence that space and time are being shattered by eruptions so vast they boggle the mind. We are just beginning to understand the impact these outbursts have had on the universe, on the shapes of galaxies, the spread of elements that make up stars and planets, and ultimately, the very existence of Earth. The discovery of what causes these eruptions has led to a new understanding of cosmic history. Back in 1995, the Hubble Space Telescope was enlisted to begin filling in the details of that history. Astronomers selected tiny regions in the sky between the stars For days at a time, they focused Hubble's gaze on remote regions of the universe. These Hubble Deep Field images offered incredibly clear views of the cosmos in its infancy. What drew astronomers' attention were the tiniest galaxies, covering only a few pixels on Hubble's detector. Most of them do not have the grand spiral or elliptical shapes of large galaxies we see close to us today. Instead, they are irregular, scrappy collections of stars. The Hubble Deep Field confirmed a long-standing idea that the universe must have evolved in a series of building blocks, with small galaxies gradually merging and assembling into larger ones. You can see evidence of this pattern by looking out into the universe. Many galaxies are gyrating around one another. Some are crashing together, others ripping each other apart. Gravity calls the tune as these galaxies draw together, exchanging stars and gas, and over time, merging to form larger composite galaxies. This came to be known as the hierarchical picture of cosmic history, in which the universe evolved from the ground up, with its structures growing larger and larger over time. A team operating at the Subaru Observatory atop Hawaii's Mauna Kea volcano examined one of the deepest galaxies known, whose light has taken nearly 13 billion years to reach us. It was a messenger from a time not long after the universe was born. This object is known as a quasar, short for quasi-stellar radio source. A small region in its center is so bright that astronomers believe its light is coming not from a collection of stars, but from a single object of at least 1 billion times the mass of our Sun. This beacon is generated by gas falling onto the object and heating up to extreme temperatures. The only thing known to generate this much power is a swirling cauldron where space suddenly turns dark as it merges into a giant black hole. For astronomers, the question was, how did this black hole get so big so early in the history of the universe? It likely got its start in an early generation of stars, often known as population 3 stars. Made up of hydrogen, they are thought to have been hundreds of times the mass of the Sun. These giant stars burned hot and fast and died young. A star is like a cosmic pressure cooker. In its core, the crush of gravity produces such intense heat that atoms are stripped and rearranged. Lighter elements like hydrogen and helium fuse together to form heavier ones like calcium, oxygen, silicon, and finally iron. When enough iron accumulates in the core of the star, it begins to collapse of its own weight. That can send a shock wave racing outward, that literally blows the star apart in a supernova. At the moment the star dies, if enough matter falls into its core, it can collapse to a point, forming a black hole. The first generations of stars and black holes burst onto the cosmic scene in a time of incredible turbulence. Within primordial gas clouds, stars were being born in dense knots. They gave rise to black holes that began to swallow more and more matter. A computer simulation of the early universe shows just how quickly these voracious monsters were able to grow. The project, by scientists at Carnegie Mellon University, was designed to recreate a region in the early universe that measured over 100 million light-years on a side. It shows what took place in the first 1 billion years of cosmic history. This virtual universe is set in motion by equations describing the properties of gas, the energy released in starbirth, and the outward motion of time and space. The result? An intricate cosmic web, with gravity drawing matter into filaments and knots, like a vast tangle of interconnected spiders' webs. Inside the densest regions is where the largest galaxies and black holes grew. Here, circles indicate the appearance of black holes deep in the data. As they gain weight by eating up their surroundings, the circles grow larger. A few in the largest galaxies reach ultra-massive proportions, billions of times the mass of the Sun. These black holes were not just swallowing gas. The orbiting Chandra X-ray Observatory was dispatched to look into distant galaxies for black holes on growth spurts. Scientists looked for pockets of gas and stars glowing hotly in X-ray light. What Chandra found was that the core of some distant galaxies contained hot pairs, twin supermassive black holes drawn together by gravity. Black holes by nature resist this dark marriage. As the two approach each other, they go into an orbit that could last virtually forever. To learn what allows them to merge, we go back to the ideas developed by Albert Einstein. He said that when massive bodies accelerate or whip around each other, they literally disturb the fabric of space, causing it to ripple like a disturbance on a pond. When these ripples move outward, they carry with them the energy of the pair's orbit, causing them to spiral closer. When this dance of death comes to an end, that's when the pair joins together to form a larger black hole. That moment may be approaching for a quasar called OJ-287 at 3.5 billion light-years away. Flare-ups in the surrounding region have led astrophysicists to conclude that another black hole is flying around it. By measuring the giant's gravitational hold on its companion, astronomers estimate its mass at 18 billion solar masses. For a time, OJ-287 was the largest black hole ever detected. It no longer is. Deep in the heart of the Coma Galaxy Cluster, a mere 321 million light-years away, lies a giant elliptical galaxy known as NGC 4889. Astronomers used several large telescopes to measure the speed at which stars are orbiting around the center. They used that data to calculate the mass of the central object. A whopping 21 billion solar masses, give or take a few billion. Theoretically, there are no limits to how much weight a black hole can gain. And yet, even the largest black holes and their host galaxies seem to obey limits. What holds them back has to do with the way clusters of galaxies evolve, a pattern long noted by scientists. This computer simulation shows the evolution of a galaxy cluster in the early universe. The gravity of the entire region draws small galaxies by the thousands, along with great streams of gas into the center. So why doesn't the central galaxy and the black hole that resides within it capture all this matter? Why don't they swallow the entire cluster? You can see the answer in a region called MS-0735. At 2.5 billion light-years away, it appears in visible light to be a typical galaxy cluster. In X-ray light, you can see that it's enveloped in a cloud of hot gas measured at nearly 50 million degrees. Hollowed out of this cloud are two immense cavities up to 600,000 light-years across. That's enough room in each to stuff 600 galaxies the size of our Milky Way. Now add in a radio image of the cluster. You can see two vast streams of matter pushing out from the center. That's a giveaway that the cavities were formed by an eruption in the core of the giant central galaxy. Two jets shooting out of a central black hole have launched blast waves that plowed through the gas that makes up the intergalactic medium. The energy it took to carve out these X-ray cavities is remarkable. The equivalent of several billion supernovae, according to one calculation. In fact, MS-0735 has been referred to as the largest single eruption recorded since the Big Bang. It was generated by a black hole that weighs in at around 10 billion solar masses. Black hole jets like this have been seen all around the universe, including in our own cosmic neighborhood. This is the famous M87 galaxy, at the center of the Virgo galaxy cluster, around 50 million light-years away. Astronomers have been intensively studying the black hole that lurks in its heart, and recently estimated its mass at 6.6 billion solar masses. It powers a pair of high-powered jets that are plowing through the galaxy. But how does a black hole, a creature famous for hiding in the dark, emit this much energy? Think of a black hole as the eye of a cosmic hurricane, kept rotating by all the stars, gas, and other black holes that fall into it. As this matter flows in, it forms a spinning donut-like feature called an accretion disk, which works like a dynamo. The spinning motion of the disk generates magnetic fields that twist around and channel some of the inflowing matter out into a pair of high-energy beams or jets. How much energy depends on the black hole's gravity and how much matter has already crashed through the event horizon. Is this just another frightening spectacle of nature? Or is it part of a more profound process at work? The largest black holes in the universe probably rose between 10 and 12 billion years ago, the age of the quasars. By releasing energy in the form of jets, they heated up their surrounding regions. This prevented gas from collapsing into the central galaxy and allowed smaller galaxies on the periphery to form and grow. But the impact of the black holes did not stop there. This Chandra image of the Hydra A galaxy cluster shows the same immense hot cavities glowing in X-ray light, as well as a jet blasting out of its central galaxy. Gas along the edge of the jet was found to contain high levels of iron and other metals, probably generated by supernova explosions in the center. By pushing these metals into regions beyond, a black hole seeded more distant galaxies with the elements needed to form stars and solar systems like ours. The black holes in these more remote galaxies then seeded their own environments. This is what might be happening in Centaurus A, also known as the Hamburger Galaxy. In X-rays, you can see a jet erupting from the center. Peering through the dense dust lanes that dominate our line of sight, astronomers have come to believe that it's actually two galaxies in the act of colliding. This computer simulation shows the effect of such a merger on black holes. As the two galaxies pass by each other, the pull of gravity disrupts their spiral shapes, forcing huge volumes of gas into their cores. As the black holes begin to feed, they emit blast waves that push much of the loose gas out beyond the boundaries of the new galaxy. In the final steps of this cosmic dance, the two black holes merge and emit one final blast. To think that our Earth, our solar system, ourselves, are the beneficiaries of these faraway monsters. The largest black holes have played dual roles in a great cosmic struggle. They are the product of gravity's relentless inward pull the force that has drawn matter into galaxies, clusters, and the structures they form. But with their incredible power, they emit energy that pushes back on gravity. In so doing, these strange and powerful objects have become the